or good afternoon, and good evening, depending on where you're at in the world. My name is Isaac Montoya, and I am the Director of Marketing here at Upside Technologies. I would like to thank you all for joining us here today for week one of our 5th annual Airflow Management Awareness Month. I'll be joined here shortly by Lars Strong, Senior Engineer and Company Science Officer here with Upside Technologies. But first and foremost, I would like to just cover a couple quick housekeeping items before I pass it off to Lars. For some of you who haven't already noticed, everybody will be muted throughout the duration of this webinar just to keep out any background noises or anything like that. But we do encourage you to ask questions. Please, feel free to submit those throughout the duration of the webinar, and we'll try to answer some of those in real time, but we will likely save the majority of them for after the presentation in the Q&A section. Also, if any of you have any technical difficulties, please feel free to send me a message through the chat box, and we'll try to get that resolved for you as quickly as possible. Both the Q&A module and the chat module are located in the Zoom dashboard. It's likely located at the bottom of your screen. For some of you, it may be at the top. So, as I mentioned, this is week one of our 5th annual Airflow Management Awareness Month. Here at Upside Technologies, we started Airflow Management Awareness Month in 2015 in an effort to raise awareness for airflow management, but also cooling optimization and overall data center efficiency best practices. So ever since then, each year we've hosted 4 educational webinars throughout the month of June on each Tuesday to try to spread this knowledge. We invite quite a few folks to come help us, teach the industry and educate the industry on some of the best practices to help data centers run more efficiently. So on this slide, you'll see our lineup for the month. Today, we are talking about Data Center Cooling 101, a beginner's guide to airflow management best practices and cooling optimization. Next week, we'll be joined by Bill Clayman, who will be talking about how to recruit and retain the next generation of data center professionals. June 23rd, we'll be joined by Mark Acton. He'll be talking about international data center standards and kind of give a nice introduction to that and how it impacts data center efficiency standards. And then lastly, we'll be closing up on June 30th with Dean Boyle and Stu Redshaw, who will be talking to us about AI and machine learning software tools and how they can help detect some of the early warning signs of cooling issues. So I think we have a great lineup this year, and if you haven't registered for those for the presentations the next 3 weeks, I'll send out a link towards the end of this presentation where you can register for each one of those. So today we will be joined here, as I mentioned, by Lars Strong, Senior Engineer and Company Science Officer here with Upside Technologies. Lars is a recognized expert on cooling optimization and holds over 20 years of experience in the field. Many of you may already know him. He holds many certifications. There's a couple listed here for both HVAC and IT specialists. He's also a recognized thought leader in the industry and has spoken at many industry events such as Data Center World, DCD events, and many others. And as you'll see here on this slide, he's talked about quite a few topics related to airflow management and cooling optimization and efficiency and everything in between, really. So without further ado, we're happy to have Lars, and I'd like to pass it off to him to get this thing started.
Thank you very much, Isaac. I want to first say that I appreciate everyone for being here and that I'm really excited to share this information with you today. We're going to cover a lot of information. And as though this is titled the Cooling 101 Beginner's Guide, this is a really important foundation for all aspects of cooling optimization, no matter how far you end up taking it in your field of expertise, whether you're managing a data center, you're a consultant, or you're working in the industry, supporting data center end users. These fundamentals are crucial to all optimization and all work that builds off of this foundation. So We'll talk about the significance of airflow management related to cooling optimization. There's a few important aspects of that. ASHRAE guidelines, of course, the relationship to PUE, bypass airflow and exhaust air recirculation, along with the 4 delta T's, are some of the most important science behind the process. And I hope to, as we go through this, to create some understanding about where some of these recommendations are coming from. There's a lot of recommendations in the industry flying around, and a lot of misconceptions and half-truths, and hopefully we'll dispel those and provide some clarification on a lot of those issues. So we'll also talk about the 4 R's of airflow management and the related best practices of each of those, and then get into the process of cooling optimization a little bit. There's a lot more we could talk about, and if people have questions, we'll do our best to answer those. And if we can't get to your questions, I do look forward to continuing the conversation with you later. So let's jump right in. I began my career working with Ken Brill. He founded the Uptime Institute and Upsite Technologies, and Ken often reminded people that it was always power in, heat out always. He used this phrase to bring awareness to the relationship between the IT load and the required cooling. If you know the IT load, basically the UPS output load, then you have a good indication of what the cooling capacity is. And that's often missed, particularly in this industry, because cooling capacity is often tracked in terms of tons. When I'm doing seminars, I often ask people if they know how much cooling they have in the room, and just about every data center manager knows how many tons of cooling they have, but they don't know what a ton is. A ton is a very tricky unit to define, not very simple and obvious, but everybody knows how much UPS output load they have. And so if we just convert to kilowatts and talk about kilowatts of UPS output and kilowatts of cooling capacity, we can compare apples to apples and have a much clearer understanding about how efficient the room is being operated. So the goal of cooling optimization and airflow management is to provide the appropriate IT equipment intake air conditions and redundant cooling capacity, of course, with the lowest possible flow rate of conditioned air. That means the fan speed's at the lowest possible speed, and with the warmest possible supply temperature of air. So the lowest flow rate of air at the warmest possible temperature. And everything is done to achieve that goal. And when this is done, a number of benefits result. Cooling capacity is increased, IT equipment reliability is increased, and operating cost is reduced as much as possible, and a number of other benefits as well. So this is kind of my career in one sentence. This is cooling optimization in one sentence. So let's look at a few of these different aspects of airflow management, because it all begins with airflow management, all the way out to free cooling and economization and data center design. It all begins with fundamentals of airflow management, and with those maximized, all the other aspects of data center operation related to cooling improve. So in a standard data center environment that is cooled with air, airflow management is simply that process of managing the flow of air through the room, all the way through the room in the complete circle. And it's specifically keeping the conditioned air separate from the exhaust air. And it doesn't matter whether this is done with cold aisle containment or hot aisle containment. Studies, theoretical and real world studies, have proven that both hot aisle containment and cold aisle containment, if done well, an important caveat, if done well, are equally efficient, can get to the same results. It's just separating the flow of air, keeping the supply away from the return. There are many configurations for IT equipment layout, and The airflow management related to those is fundamentally the same. I'll be talking about a lot of different concepts today, and whether you have hot aisle containment or cold aisle containment, and even if you have a slab environment, most of the conversation will apply. Most of the science applies to all of those different configurations. The benefits, as I mentioned, of improving airflow management, they can reduce IT equipment intake air temperatures. Getting rid of hot spots is one of the first and most important things to achieve. You know, every data center in the world can be classified into one of two conditions: data centers that are providing appropriate intake air temperatures and those that are not. So if a data center is not providing appropriate intake air temperatures, then that needs to be fixed right away. But if all the intake temperatures are appropriate, no hot spots, no cold spots, then the question is, can it be more efficient? Can airflow management be improved so that cooling optimization can take place and operating costs can be reduced? It's important to understand that airflow management is not going to reduce operating costs. We'll talk about this more as we continue. But improving airflow management creates an opportunity to adjust the cooling controls and the set points to reduce the operating cost, improve the cooling capacity, defer capital expenditure, and all the other benefits that, that fall out of that. So we're all familiar with this picture: hot aisle, cold aisle. What's important to notice about this image, though, is that it's an ideal configuration. We have just the right amount of air being delivered into the cold aisle. All that air is sucked up by the IT equipment. There's no excess cold air leaving the cold aisle. We have no cold air coming out of any other openings in the raised floor. This is a perfect situation. However, airflow management is invisible. Air moves and we can't see it. So unfortunately, this is the reality of what's going on in many computer rooms. And just a few things to point out: we have air coming out of unsealed cable openings underneath the cabinets. There's some misplaced perforated supply tiles in a hot aisle or maybe out in an open space in the room. And we've got exhaust air recirculation over the tops of the cabinets or maybe around the ends of the rows. And all of these things reduce the efficiency in the room and take up capacity. And by improving these things, we can recover that stranded capacity. So where do we start? It all starts with the intake temperatures to the IT equipment, because after all, that's one of the fundamental reasons that a data center exists. A data center exists for three primary reasons: continuous power, continuous availability, and continuous cooling. And of course, security and a few other things, but those are the three primary things. So in our world, what we're talking about today, it's about cooling and providing the appropriate environmental conditions for the IT equipment. ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers, their guidelines for environmental conditions are the most widely followed around the world. And it's important to note that what they're talking about with these temperatures is the intake air conditions for the IT equipment. No other location in the room is as important. No other location in the room is what these parameters are referring to. It's all about the intake air temperatures to the IT equipment. So as we well know, for all server classes, the recommended temperature range is from 64.4 to 80.6, and that comes from a nice round Celsius number of 18 to 27 degrees. And that's the recommended. However, for various server classes, the allowable increases for the higher server classes. There has been a trend, an evolution in the industry, that server classes are increasing. For example, Dell servers introduced to the market since 2014 are all class A3. This means they have an allowable intake air temperature of 104 degrees Fahrenheit. And many of the servers that are produced in the last 5 years are warranted up to 95 degrees Fahrenheit, 35 degrees Celsius. And many of them are warranted up to all the way up to 104 for Class A3. So depending on the mix of the equipment, it's important to recognize this and see that intake air temperatures can be driven much higher than most people are doing. It's also important to note that the manufacturers of the IT equipment don't put limits on the amount of time that the equipment can operate at the upper limits of the allowable inlet temperatures. It's still warranted. That doesn't mean that everybody should be running their data center with inlet temperatures of 100 degrees, but it does mean that there's a lot more room. Of course, you know, for those operating colos or having their equipment in colos, you know, SLAs are often have much lower requirements, or a lower temperature threshold, that is, and that's going to govern the maximum inlet temperature that the data center can be operated at, of course. But for those with more freedom to adjust, there is room to increase the temperatures with a very small increase in compromising the reliability of the equipment. But the benefits, particularly if airside economization is used, can be really dramatic. So this is, again, the situation that most of us are facing to some degree or another. Of the hundreds of data centers I've been in, there's probably been less than a handful that couldn't be improved any further. That's a very small percentage. Almost every data center I walk into has some amount of exhaust air recirculation, some amount of bypass airflow that with improved airflow management can be optimized further and the operating costs can be reduced. So let's look at how this plays out with PUE. Now, probably everyone on this call is familiar with PUE, and if you're not, we'll go through it at a high level so you have an understanding, because it's a really important concept. It's a metric that has gotten the most adoption around the world, again, and it is defined as the power usage effectiveness. And there's a direct relationship between airflow management and PUE. When we look at how power is consumed in a data center, this pie chart represents all the power consumed, the total load of the entire data center. And PUE is simply taking the total load and dividing it by the IT load, the power going to the IT equipment. And for this example, we have a PUE of 2. The IT equipment represents about half the load, so the total divided by half gets you to a PUE of about 2. And when you look at how this breaks out, when you look at the power required for the mechanical cooling and the cooling fans, this represents 35% of the total load, but a whopping 73% of the non-IT load. That means that improving the efficiency of the cooling is the greatest point of leverage in reducing the operating cost, improving the PUE, and regaining stranded capacity. And you know, when you look at the other loads, such as electrical losses and lighting, you know, there may be a very good business case for improving the efficiency or replacing a UPS system, but that's affecting a relatively small portion of the pie. The greatest leverage exists in the cooling optimization, and the way to start there is by airflow management. It starts with something as simple as blanking panel use. So let's get into some of the science and some of the terms. Bypass airflow is a concept that's been widely thrown around in the industry. The Uptime Institute coined this term many, many years ago, and I participated in the research that developed that white paper and found just how poorly the airflow was being managed in computer rooms. And that term has stuck, and and yet it is fairly misunderstood. It's very important to consider bypass airflow at the room level. The concept is simple, that bypass airflow is any conditioned air that leaves a cooling unit and does not pass through IT equipment before returning to the cooling unit. The purpose in life of a molecule of air that comes out of a cooling unit is to pick up heat from IT equipment and return that heat to the cooling unit. And if it doesn't flow through IT equipment, it's missed its purpose in life, and it's bypass airflow. It's simple to calculate. The concept, anyway, is very simple. Bypass airflow equals the total airflow through all the cooling units minus the total flow rate through the IT equipment demand flow rate. So the total moving through the room minus the amount that is required by the IT equipment, the balance is bypass airflow. Pretty simple. However, it often gets misunderstood. In this diagram, we see how the airflow is moving through the room. We've got the air moving through the cooling units, going under the floor, and air is going to come out of any opening under the floor, regardless of whether it's in a good location or a bad location. And in this example, we've got some bypass airflow coming out of unsealed cable openings. We've got some conditioned air coming into the cold aisle where it should. However, the amount coming into the aisle is greater than the amount required by the IT equipment. So the excess leaving the aisle is bypass airflow. We'll talk about this more as we continue later in the presentation. Exhaust air recirculation. We know it's all a bad thing. Obviously, when exhaust hot air recirculates to the inlets of IT equipment, it raises the IT equipment intake air temperature. And it can be mitigated by using more conditioned air or a lower temperature, having higher fan speeds or having colder set points. This often shows up in reverse, meaning that when people go to do optimization, they try to improve the fan speed and they try to improve the set points, and they have to stop at a certain location because if they turn down fan speeds any further, there will be problems created. But if the airflow management is improved, then fan speeds can be reduced even further, set points can be raised. So exhaust air recirculation shows up in a number of different ways. We got the obvious ones here around the ends of the cabinet rows. When, of course, this exists when there's no doors on the ends of the aisles, over the tops of the cabinets. Of course, when there's no roof or there's no baffles on top of the cabinets, air can flow over the tops of the cabinets. Through the cabinets, when air circulates without ever leaving the cabinet. It doesn't even go out of the back door, it just flows through spaces, through a missing blanking panel and into inlets, or underneath cabinets. And this is an often overlooked location. That space created by the levelers and the casters creates a path for exhaust air to flow under the cabinets and into the cold aisle. And many times I find the highest inlet air temperatures are in the bottom couple of view of the cabinets. Let's start talking about the 4 delta T's. So delta T is a obvious concept. It's simply the change in air temperature. And if you ask somebody, what are the delta T's in a computer room? It depends on what their background is, what their response will be. So the obvious ones are the change in air temperature through the cooling units and the change in air temperature through the IT equipment. However, there's actually 2 more, and they're very important to understand because they can provide a lot of insight into the potential to optimize the computer room. So let's look at those. Here we have we'll start with the ideal scenario here, showing the airflow through the room, and we see the hot air coming out of the IT equipment and not cooling off much as it goes back to the cooling units, the same temperature. We see a big delta T as the air goes through the cooling unit, And then we see the air from the cooling unit flow out and go to the inlets of the IT equipment, again with very little increase in temperature. The big increases we see are at number 1 and number 3. The change in air temperature as the air flows through the IT equipment and picks up heat, and the change in temperature as the air flows through the cooling unit and gives off its heat to the cooling unit. However, that is not the case in most computer rooms. In most computer rooms, these other two locations, delta T2 and delta T4, have very substantial delta Ts. When we look at what these temperature changes are, delta T1 through IT equipment, you see it's represented here from green to red, somewhere from 75 to 95 degrees. Air is often coming out of the back of servers in over 100 degrees, depending on the inlet air temperature, and also depending on the design of the IT equipment. Generally, you can consider that IT equipment has about a 20-degree delta T. Some have significantly higher delta Ts, 30, 40 degrees Fahrenheit delta T. But at 20-degree delta T, it requires about 156 CFM to cool 1 kilowatt of IT load. Then that air comes out quite hot, might come out at 100 degrees, but it returns to a cooling unit at, say, 70 degrees. So why has the air temperature dropped 30 degrees from the time it left the IT equipment? Well, the obvious answer is that conditioned air, bypass airflow, cold air that never passed through IT equipment and picked up any heat, has mixed in with that air and cooled it off before it returns to the cooling unit. That conditioned air might be coming out of cable openings or misplaced supply tiles, or too much conditioned air delivered to a cold aisle coming out and mixing in. And that 30-degree delta T is an indication of that bypass airflow. On the supply side, we see the air coming out of a cooling unit, and it might be 65, 70 degrees in a good case. Ideally, it should be closer to 75, 80 degrees, very close to the maximum inlet air temperature of the IT equipment. But it often comes out at somewhere around 60 degrees. And yet, the warmest inlet air temperature to the IT equipment is often 75 to 80 degrees or even higher. So why has the air temperature increased 20, 30 degrees from the supply to the warmest inlet of IT equipment? Obviously, exhaust air recirculation has mixed in with that supply air and raised the temperature before it gets to the IT equipment. So these two other delta Ts can be pretty easily measured, just with an infrared thermometer or an infrared camera, or various other temperature measuring devices. And while it's tricky to get these accurate, the value in knowing about these other two delta Ts is that they're easy to get a ballpark figure on what they are. It's not important whether it's 30 or 31.2 degrees. The goal here is to have this delta T at 5 degrees. That's about the point of diminishing returns. So if you might go and measure this delta T and you find it's 20, 30 degrees, there's a lot of room for reducing the amount of bypass airflow in your room. And if you go and measure the difference in the supply temperature to the maximum inlet air temperature, and again, that's 20 or 30 degrees, then there's a lot of room for improving airflow management to block the exhaust air recirculation in the room. So to help guide this process, we've developed the concept of the 4 R's of airflow management. The 4 R's is a holistic approach that helps bring awareness to the process, that airflow management can be improved at each of these 3 areas around this outer circle here. You can improve the airflow management through the rack, you can improve the airflow management at the row level, and improve the airflow management at the raised floor level. And once those are done, changes need to be made at the room level to realize the benefits, to realize the cooling capacity and operating savings benefits. Airflow management improvements in this outer ring at these levels can produce the benefits of reduced inlet to air temperatures, elimination of hot spots, but it's changes at the room level that are required to reduce operating costs. So let's look at each of these different areas and what some of the best practices are. Rack airflow management is managing the airflow through the vertical plane across the face of IT cabinets. There's a lot of misconception in the industry that it's necessary to have side panels and prevent air from flowing side to side through the cabinets, or some people have even installed blanking panels on the backs of the cabinets. There are very rare cases where that might be a good idea, but generally, it really only needs, airflow really only needs to be managed at that front vertical plane across the face of the equipment. There should be no opening in this vertical plane all the way down to the floor, except for the openings in the inlets of IT equipment. So, rack airflow management best practices are installing blanking panels in every open use space. And this really should be bolded and capitalized and italicized, every open use space, every single one. Sealing the spaces between mounting rails and the sides of the cabinets, this is often overlooked. So the design of some cabinets leave large open spaces there. Identifying IT equipment that's mounted to the back rails. Commonly switches are mounted on the back rails, and even though they breathe front to back, the inlets are buried inside the cabinet because they're not full depth. The switches are on the back rails, and so the inlets can't get to the cold air in the cold aisle, and these need passive channels to help duct that conditioned air from the cold aisle to the inlets. And then, of course, identifying IT equipment that's facing backwards and get that switched around. Make accommodations till it can get switched around, and in best cases is putting processes and procedures in place, policies in place that are enforced, so that IT equipment doesn't get mounted backwards, and that compromise to the efficiency isn't seen. Let's look at the raised floor airflow management. Of course, we're talking about the horizontal plane now of the raised floor, and managing every open space in this horizontal plane. There's two aspects to this, and they come in the form of sealing all the open spaces other than the supply tiles, and then managing the type, the location, and the number of supply tiles, making sure that the right amount of conditioned air is delivered to the cold aisle. There's other ways to do that as well, of course, with fan speeds, but as far as airflow management goes at the raised floor level, we want to get all the cable openings sealed under equipment, under the electrical equipment, making sure supply tiles are in the right locations. The best practices are sealing the cable openings with brush grommets, sealing around the perimeter of the room, making sure there's no pass-throughs through the perimeter walls, making sure that the spaces under behind cooling units or under RPPs, remote power panels that are distributed around the room, that those are sealed. Those are often creating large openings in the raised floor. Make sure the supply tiles are properly located. There's no need for a grill if a 70% open area grill if there's only 5 kilowatts in the cabinet. Making sure that the amount of air being delivered is appropriate for the amount of load that is needing to be cooled. At the row level, improving the cold aisle airflow management or the hot aisle airflow management is done with doors, obviously, and baffles or roof. And this is one of the questions that I often get, and someone may have asked already, is if I have a limited budget, where should I spend my money first? And first, the place to do is to address rack airflow management, and then move on to row airflow management, and then last, start spending money improving the row airflow management. That looks like blocking open spaces underneath the racks. That's the spaces created by the casters and the leveling feet that I mentioned. Sealing spaces in the cabinet rows, such as where there's a missing cabinet or there's a column that's prevented the location of a cabinet. Installing aisle end doors on either the hot or the cold aisle, and installing some form of blockage on top of the cabinets. Very often, a full roof is not necessary. All that is necessary is a partial blockage, a baffle across the tops of the cabinets to prevent that exhaust air recirculation, and cooling can be optimized. Now looking at room airflow management, we're talking again about the optimization process. Changes at the room level are required to realize the benefits of all that airflow management work that's been done, all those products, those things that have been put in place. Once that's done, we can make changes at the room level to realize the energy savings and the myriad of other benefits. And this begins the process of cooling optimization. So the best practices of room airflow management and cooling optimization are raising cooling unit air temperature set points as high as possible without exceeding the maximum allowable IT equipment intake air temperatures. So there's been a lot of controversy in the industry about raising temperatures. People say, I don't want to raise the inlet temperature to my IT equipment for various reasons. But if airflow management is really done thoroughly, then intake temperatures to the IT equipment are reduced. Then the set points can be raised and the intake temperatures return to where they were before, but with higher set points on the cooling units. And then we have more efficient cooling units. Reducing fan speeds as much as possible with variable frequency drives, and the fan affinity laws, fan curve laws really produce some valuable benefits from reducing fan speeds. Expand the allowable relative humidity range. This is being done in many data centers, especially if airside economization is being used. Outside air is being brought into the room. It's not possible to tightly manage that relative humidity. And IT equipment is robustly designed to handle a wide range of relative humidity, and many people are really letting go of that relative humidity control. It's also very important for efficiency, because if you have each individual cooling unit managing relative humidity to a to a narrow band, then it's quite possible for cooling units to be fighting each other. One cooling unit to be dehumidifying and the adjacent cooling unit to be humidifying. And this just is consuming energy in a number of different ways. If variable speed drives are not, variable frequency drives are not installed on cooling units and fan speeds can't be reduced, then turning off cooling units is possible once airflow management has been improved. This is one of my favorite things to do, is turn off cooling units. Turned off a lot of cooling units in rooms, and very often conditions actually improve. Airflow management is improved because bypass airflow is reduced, cooling units can sense the load that's in the room, and conditions get better with fewer cooling units running. So let's talk a little bit more about the process of cooling optimization. I've already mentioned this in a number of different ways as I've been going through the slides so far, but it's important to reiterate. It's the process of making adjustments to the cooling system controls to improve energy efficiency. And again, the benefits are myriad, and what's important to you varies. It could be costs, it could be cooling capacity, could be IT equipment reliability, getting rid of hotspots, or deferring capital expenditure. There's many business cases where improved airflow management what prevented the construction of either a new data center or a substantial remodel addition to an existing data center. And the value of the savings of deferring those massive capital expenditures can be enormous. Or even if it just means deferring the capital expenditure for buying another cooling unit. Most data centers have way more capacity than they need. It's just a question of utilizing that capacity that's already been installed more appropriately. It's an iterative process. Very rarely do you make adjustments and you're done. Adjustments to optimization need to be done incrementally and slowly to make sure that changes don't cause any problems. And as equipment changes in the room, rooms are dynamic. As IT equipment goes or is added, load shifts and changes. The cooling units rarely are capable of making the full adjustments to realize the energy efficiency benefits that can be achieved. Most cases, some intervention is required in understanding the process in the room, understanding these fundamentals that I've shared with you, enables you to go in and make those adjustments to realize those benefits. And, you know, as I said, any significant change in a room is an indication that optimization could be done. And it's often when equipment leaves a room that optimization is potential is there. Without cooling optimization, I'm going to keep beating this home, that airflow management improvement is largely an expense. It's making those adjustments that achieve the benefits. Efficiency can't be purchased. It has to be managed, and intervention has to be done. So let's revisit again that very important concept of bypass airflow and how this works. So now in these diagrams, I've added some numbers, and these numbers represent the volumetric flow rate, or the flow rate of air. So in the United States, the unit that is most common is CFM, cubic feet per minute. These numbers are much greater. You know, a single cooling unit might have thousands of CFM, but just for comparison's sake, we'll just look at these simple numbers. And so in this room, we have a total of 10 units of air moving through the cooling units. So if you add up all the air coming out of all the openings, there will be a total of 10 units of air. And in this case, we have 6 units coming out of the supply tiles in the cold aisle, and 4 units of air coming out of unsealed openings under the cabinets, 2 in this row and 2 in this row. We have in this row of cabinets, the IT equipment consuming 2 units of airflow. And in this row of cabinets, another 2 units of airflow is consumed. So with 6 units of conditioned air delivered to this cold aisle, 4 units is sucked up and consumed by the IT equipment, leaving 2 units of conditioned air leaving the cold aisle as bypass airflow. We also have another 4 units of bypass airflow from these unsealed cable openings. So there's a total of 6 units of bypass airflow in this room. And this is very, very common, even conservative numbers for most computer rooms. Many computer rooms have much higher ratios of bypass airflow. And when you look back at the equation, it's simply the total airflow through the room, 10, minus the amount going through the IT equipment, 4, leaves you with 6 units of bypass airflow. By improving airflow management in the room and sealing the cable openings in this example, all 10 units of conditioned air is now delivered to the cold aisle. However, the IT equipment still only requires a total of 4. We still have 6 units of bypass airflow in this room. And many people would look at this diagram and say, well, all you do is you need to just put a roof on there and put doors on the aisles, and you'd block that 6 units of bypass airflow. And that's not actually the case. You would prevent the air from leaving the aisle out the top of the aisle, but you wouldn't change the amount of bypass airflow in the room. This extra 6 units of conditioned air would just be forced to flow through the IT equipment when it's not needed. It is essentially still bypass airflow. So now that we've improved the airflow through the room, we've done all the airflow management methods, blanking panels, sealed the raised floor, put doors on the ends of the aisles and baffles or a roof on top of the cabinets. We now have the ability to reduce fan speeds or turn off half the cooling units in the room and realize those benefits. We'll turn it down not all the way to 4, but to deliver 5, have a little extra conditioned air, to have a little buffer for variations in IT demand and slight positive pressure in the aisle. But now from an airflow volumetric flow rate perspective, the cooling has been optimized. So let's take a look at some of the key takeaways. Airflow management can have a profound impact on the data center's cooling strategy, the overall cooling capacity, and the IT equipment reliability. Improvements at the rack, the raised floor, and the row levels are necessary steps to improving IT equipment inlet air temperatures, but alone do not save you money. You got to make those adjustments. Improving IT equipment inlet temperatures enables the opportunity for the changes to the infrastructure to realize those benefits. Airflow management and cooling optimization is an iterative process. So remember the 4 R's and pick one of those R's and really make an effort. That's my recommendation. Really make an effort. Focus on, say, rack airflow management. Do everything you can to button up the rack. Then check in at the room level, make adjustments to realize the benefits. And when time and money are available, take a look at another one of the R's and go through that iterative process. Some other benefits of airflow management and cooling optimization are the reduced operating cost and increased cooling capacity, improved IT equipment reliability, the reduced infrastructure maintenance costs. For example, if you turn off half the cooling units in the room, you can take those off the maintenance contract. When you are able to increase the supply temperature of the conditioned air, if there's airside economization or some other free cooling methodology, this can have a profound impact on the number of hours that free cooling is available and can dramatically improve the business case for those free cooling techniques. We haven't left the computer room in these conversations, but making improvements to the airflow management and the cooling optimization in the computer room creates the ability to increase the chilled water set points, which can have a substantial impact on the operating cost of a facility. Chillers, if a facility is using chilled water systems, those chillers consume a great deal of energy and they become more efficient at the higher the chilled water temperature. For co-location facilities, airflow management is becoming an absolute requirement for being competitive in the industry because of the ability to support more customers in a given space, to honor SLAs, and to be sure that what has been sold can be delivered. And of course, deferring capital expenditure for additional cooling units or new data center builds can be a very, very substantial number. So with that, we've gotten to the end of the content. I really appreciate your time, and now we'll spend some time answering as many questions as we can.
All right, thank you, Lars, and great job. Just to cover real quickly, we've got a few questions about if a PDF will be available for this presentation. And the answer to that is yes. We will also be sending along the recording just in case you would like to watch this again. So let's jump into the questions. All right, first one. There are different airflow directions in a server. Has the Uptime Institute taken initiation to follow standard air in-out direction in a server. I'm not sure if that's a question we can answer for the Uptime Institute, but Lars, what do you think about different flow directions in servers?
Yeah, there's a few things I can say about that. You know, obviously, some manufacturers of IT equipment pay attention to this more than others. The standard does exist in the industry, not necessarily by the Uptime Institute, but just the standard is, you know, flow from the cold aisle to the hot aisle, and more manufacturers are getting on board with this process. That as I mentioned, can be problems can be created by people that mount the equipment backwards. Sometimes that's just a lack of understanding of the process, and it really points to the importance of making sure that both IT sides of the business and the facility sides of the business have a shared understanding about the process and how cooling works, how cooling airflow optimization works, and what is necessary to follow those best practices.
All right, thank you, Lars. Let's move on to the next one. From a thermal storage point, is there any difference in cold aisle or hot aisle?
Yeah, so what I believe this person is asking about is thermal storage and the mass of the thermal mass of cold air, of cold stuff versus hot stuff, and the benefits of having more thermal mass, more cold thermal mass if there's a cooling failure. And so when you do cold aisle containment, you minimize the cold thermal mass in the room. Just the cold aisle is cold and the rest of the room becomes hot. When you do hot aisle containment, just the hot aisle is hot and the rest of the room is cold. And so yes, long answer to your question, there are some thermal storage benefits of doing hot aisle containment versus cold aisle containment.
All right, thanks, Lars. Next question. In the PUE calculation, the UPS losses from input to output is added to the total load, the IT load, or is it not considered at all?
That's a good point. And so there's a number of different levels of actually calculating PUE when you get into the detail. And one very, you know, call it the quick and dirty way, is to just take a look at the UPS output load. And that'll give you a ballpark number. But I appreciate Mauricio bringing up this point, because there are other losses. There's the distribution losses of the power through the cables after it leaves the UPS, and then there's potentially conversion losses in the RPPs that are in the room. And so the most accurate way to calculate PUE is by summing the loads at the PDUs in each of the cabinets and comparing that to the total load in the facility. The difference between the UPS output and that is relatively small, so it is a question of how much effort do you want to take, and how accurate do you want to be.
Thanks, Lars. We have another one here related to PUE, and it's not much of a question, but I think it adds to what you were just saying. PUE could be a live parameter. It's often quoted as a seasonal or annual number. Real-time analysis utilizing all air data halls has some very low PUE values with low outside air temperature.
Yeah. So there's some more good points are being brought up. Appreciate them. So PUE. There's both instantaneous and then trailing average. There will obviously be some variation in the amount of cooling required by the season, and appreciate this listener, you know, bringing this point up, because one of the things I mentioned was heat load in the room, and power in, heat out always. And if you know your UPS output load, you have a good idea of what the cooling load is. And that's generally true, but depending on the room, there may be building envelope load If the walls of the computer room are exterior walls and the walls are not very well insulated, or the ceiling in particular is not very well insulated, then in a hot environment in the summer, there can be a substantial amount of heat coming through the walls, the ceiling, and adding to the heat load. And that's why variations in the PUE are exist, and why a trailing average for PUE is often a better indicator of instantaneous PUE.
All right, thanks, Lars. Got one here. How can you monitor delta T?
Delta T's, the 4 of them. So we'll start with number 1, the delta T through the IT equipment. That's pretty easy to measure with a, measuring the temperature at the inlet and then measuring the temperature at the exhaust of the IT equipment. So that can be done for individual pieces of equipment. It can be done at a row level, at a more of an average and a slightly less accurate level by using infrared thermometers or infrared cameras. Measuring the delta T from the back of the equipment to the return to the cooling unit can be done by simply comparing the average exhaust air temperature from the equipment with the return air temperature conditions at the cooling unit. And the return air temperature conditions at the cooling unit, as well as the supply air temperature from a cooling unit, are often provided on the display of the cooling unit. So that's obviously the way you can get the delta T through the cooling unit. But the ones that are most important that give you the indication of improvements are the exhaust from the equipment to the cooling unit, and then the supply from the cooling unit to the warmest inlet of IT equipment. And that again is very easy. You just look at the display for the cooling unit and you can know what the supply air temperature is, or measure it if it's an older cooling unit that doesn't tell you the supply air temperature, and then compare that to the warmest inlet air temperature to the IT equipment, and that'll give you that delta T. And what I want to emphasize is that the goal there is 5 degrees Fahrenheit or 3 degrees Celsius is the goal for those other 2 delta T's. That the air temperature should only drop 5 degrees from the time it leaves the server on average, the average exhaust air temperature to the cooling unit, and the air temperature from the cooling unit to the warmest inlet of IT equipment the goal is to be 5 degrees.
All right, thanks, Lars. Got another one here in terms of monitoring or measuring temperature. How do you measure the temperature and airflow if the CROGs, the air handler, are modulating? Do you take an average of the measurement?
Yeah, so of course there's instantaneous and average considerations for all these. And there's fluctuations in the IT equipment. So instantaneous is quite often very insightful and gives you some indication, but if there are large variations, then you do need to take those into account and make those measurements at the 2 different extremes. Yeah, good point.
All right, thanks, Sergeant. We've got quite a few questions here. We're going to try to get to as many as we can. If we don't get to them for whatever reason, we will follow up with you after the presentation. So move on to the next one here. Is rack or raised floor airflow management necessary if containment has been installed?
Yeah, absolutely. If containment's been installed, then there's been some benefits have been realized from the installation of the containment. And hopefully some optimization has taken place and fan speeds have been reduced and set points have been raised. But if the rack and raised airflow management are improved, then those benefits can be even greater. More adjustments can be made, fan speeds can be reduced even more, and set points can be raised even more. So absolutely, all the R's are very crucial for maximizing the efficiency and reducing the operating cost.
All right. Let's quickly move on to the next one. What are your thoughts on adding fans where supply air openings are located when air is not enough?
Yeah, so Tommy, good question. You're referring to the fan-assisted supply tiles. And I've generally said that somewhere around 80% of fan-assisted tiles sales have been inappropriate, meaning it's a waste of money, and it actually just increases the heat load in the room and the complexity of what's going on. And it worsens the conditions. When you put in a fan-assisted tile, the airflow in the surrounding tiles goes down because more air is coming out of that one location. Fan-assisted tiles don't create airflow. There's a finite amount that is defined by the amount of air that is going into the raised floor from the cooling units. And so if you pull it out in one location, you take it away from another. So the solution for those 80% of locations when fan-assisted tiles are not a good idea, the reason that is there's a lot of unsealed cable openings. And if those cable openings and openings under PDUs and other perimeter openings, if all those were sealed up tight, you'd get more than enough air out of those locations to take care of the need in almost all cases. That leaves that 20%. When it's a low raised floor, maybe there's a lot of blockages or it's a long way from cooling units, there are certain situations when there's just not enough air, and a fan-assisted tile is a good idea.
All right, thank you, Lars. Unfortunately, we are over the top of the hour here, so I do apologize if we did not get to your questions. Like I said, we will follow up with you after this presentation. Also, if you have any questions that you think of here after the presentation, feel free to email Lars. Or you could email me. You could just simply send an email to marketing@upsite.com. I'd like to thank everybody for joining us here today. We will be sending out the PDF slides and recording within the next couple of days. Lars, thank you so much. You did a great job.
Thank you, everyone. I really appreciate your time for joining us and look forward to any follow-up questions.